We will look at the chapter 2, section 4, and chapter 2, section 4 is called Measures of Variation. This is a quite long lesson, and we'll try our best to squeeze it in one video. We have 5 objectives with this lesson. We want to learn how to find the range of a data set, and we want to find the variance and standard deviation of a population and a sample. And then we're going to use empirical rule and Chebyshev's theorem to interpret the standard deviation. Fourth will be approximating the sample standard deviation for group data. And then the fifth objective here is use the coefficient of variation to compare variation in different data sets. Out of all these objectives, the easiest one is finding the range. Range is the difference between the greatest number in your data set and the smallest number. So when we have two corporations here, the first one represents the salaries in corporation A, and the second one represents the salaries in corporation B. And if we want to find the range for both of these institutions, so range is you're just going to find the minimum number here. So when I look at these salaries, the minimum one here I see is $47,000. And the maximum one here, that 57 is the largest one. So the difference between 57 and 47, which is 10, that will be the range for corporation A. That's how we find the range for a data set. You find the maximum number and the minimum number and subtract them. So variation is a very important concept in statistics. Both data sets in the last example have a mean of 51.5. You know, in order to find the mean, you add all the different salary values and you divide them by how many you have them. So for both of these companies, the mean is 51.5, meaning that it's 51,500. And their median is 51 or 51,000. And a mod is 51. That means that's the salary shows up the most. But these two sets differ significantly. The difference is that the entries in the second set have a greater variation. As you can see in the figures on the next slide, the starting salaries for corporation B are more spread out than those for corporation A. So when you look at the corporation A, the salaries are accumulating between these 3 bars, but for corporation B, there is even a person who has a salary of 35.5, and there's another person who has a salary of 65.5. But here, majority of the salaries are accumulated between these numbers. So they have different variation. So we're going to look at what deviation means. So we're going to understand the definition of deviation, variance, and standard deviation. Deviation means the difference between the data entry, X, and the mean of the data set. So since population mean is represented by mu, and sample mean is represented by X bar, in order to find the deviation for population, we need to do whatever the data value is minus mu. For a sample data set, we're going to find the deviation by subtracting the X bar, which is the sample average, X minus X bar. That's how we find the deviation. So population variance will be, so variance means sigma squared. Population variance will be X minus mu. So we're going to subtract the mu value from each data points, and then we will square each one, and then we will add them up, and we will divide them by how many we have. For population standard deviation, we're just going to take the square root of this number. So as you see here, this formula is no different than the other formula, but you are taking the square root of that formula. Observations about standard deviation. The standard deviation measures the variation of the data set about the mean and has the same units of measure as the data set. The standard deviation is always greater than or equal to 0. When sigma is equal to 0, the data set has no variation and all entries have the same value. So this is a very important point. When there is no different data points and all of the data points are the same, that means your sigma is equal to 0. So here, sigma stands for standard deviation. As the entries gets farther from the mean, that's more spread out, that means your standard deviation is increasing, your sigma is increasing. So finding the population variance and standard deviation. There's a lot of steps here, but these days, actually, Excel and some other technology, they are going to help you to do this work, finding the standard deviation. But what is important as a statistician will be understanding the meaning behind the standard deviation. But generally, to find the variance in standard deviation, first thing you do is you find the mean of the population data set. So you divide the sum by how many data sets, how many data points you have. Then you're going to find the deviation of each entry, which is x minus mean. And then you will square each deviation, and you're going to add all these deviations from each data point. And then you're going to divide them by n to get the population variance. Find the square root of the variance to find the population standard deviation. So finally, sigma is calculated. Find the population and variance and standard deviation of starting salaries for Corporation A listed in the first example. So if we go back a couple of slides, so here we had this Corporation A as a table, which had 10 data points. And we're going to now, using the data set, we're going to apply the steps to find the variance and standard deviation for this company. So we know that there are a total of 10 data points. So first, and the sum for all those salaries is $515,000. So the average, the mean is this number divided by 10, which is 51.5, which was listed as the first step to find the standard deviation. You always find the mean of your data set first. Then you're going to find the deviation for each data entry. So the mean, according to the previous slide, is 51.5. For all of these 10 salaries, you're subtracting your mu value from each of these points, and sometimes you're finding a negative number, sometimes you're finding a positive number. And then you're just going to go ahead and add all these numbers. And interestingly, when they add all these numbers here for this example, the sum is equal to 0. So x minus mu, so these numbers, when you add them up, the sum is a 0. But then for these differences, if you square each one and then add them up, the sum is 88.5. So 88.5. Now for the variance, you're gonna divide 88.5 by 10, which becomes 8.9. And for the standard deviation, you're gonna take the square root of this number, which is about 3, because this number is very close to 9. Taking the square root of this number is gonna give you almost 3 as the population standard deviation. The population variance is about 8.9, and the population standard deviation is about 3 or 3,000. Sample variance. It's really the same thing with all the steps as the population. The difference is, as you know, for sample, the average, we don't call it mu anymore, we just call it x bar. So variance is really the almost same formula as the population variance, but instead of dividing by n, we just divide by n minus 1. And for the sample standard deviation, you still take the square root of your variance, which will be the square root of this formula. And then for finding the sample variance and sample standard deviation, you are applying the same steps as the population. Okay, the only difference is instead of dividing by n, you're going to divide by n minus 1. So you will be able to find your sample standard deviation. So here's an example to understand these steps. In a study of high school football players who sustained concussions, researchers placed the players in 2 groups. So we have group 1 and group 2. So find the sample variance and standard deviation of the recovery times. So we have this data set. It has 8, 10, 4, 6, 7, 7, 9, 10, 7, 6, 5, 11. And this is a sample. And for the sample, we're going to find the variance and standard deviation. So it's just like the other population thing. First thing is we're going to add all these numbers, and then you will divide them by how many you have to find your X bar. And then you will subtract your X bar from this number to find your X minus X bar. So here, if you add them all up, you get a 90, and you divide them by 10. Is it 10, 2, 4, 6, 8, 10, 12 actually? So yeah, so their sum is 90. We have 12 data points. So the X bar is 90 divided by 12, which is 7.5. And on the previous page, if you subtract 7.5 from all these numbers, you get your deviation. These are called deviations. X minus X bar is called deviation. And then you square all of these numbers to find the X minus X bar squared. And when you add them up, your sum is 51. And then 51 is not going to be divided by 12. It's just going to get divided by 1 minus n minus 1. So it's 12 minus 1, which is 11. So variance is 4.6. To get the standard deviation for this sample, you need to take the square root of 4.6, which is about 2.2. The sample variance is about 4.6, and the sample standard deviation is about 2.2 Bells. So using the technology to standard deviation, sample office rental rates in dollars per square foot per year for Los Angeles are shown in the table. Use technology to find the mean rental rate and the sample standard deviation. So we have all these numbers now. When it says technology, it changes depending on the year that you're actually doing this class. These times, like Excel is really good about any data related profession. So if you know how to, if you enter these numbers on Excel and then go to the data tab on Excel, you can find the data values for this question. Also, I do use one of the software called Alteryx. It's my all-time favorite software. It just helps you very much about the variance and standard deviation. So there is something also with Minitab. For Minitab, when you enter those values, it's going to give you the mean and it's going to give you standard deviation, or Excel will give you the mean and standard deviation in this format. And this is how you're going to find, how you're going to see these values on a TI-84 calculator. If you have one, it's going to give you the X bar and S of X. I will also give you guys a video to calculate the standard deviation using Excel after this video. Now, interpreting standard deviation. Standard deviation is a measure of the typical amount an entry deviates from the mean. The more the entries are spread out, the greater standard deviation is. So we have 3 shapes here. And then when we look at these 3 shapes, on the first one, although there are a total of 8 different data points, they were actually not different. Their value is always a 5, so we're just taking one number for all of the data entries. The average is the same as your data entries, which is 5, but S is here equal to 0 because there is no difference between these data points. When we look at the second one, it's like a more uniform type shape. Yeah, it is very obvious that we have more data, which is equal to 5. We have total of 4 data points whose value is 5. But among these 4 points, we have also 2 data points whose equal to 4, 2 more data points whose equal to 6, 1 data point is equal to 3, 1 data point is equal to 7. So for this one, the average is still the same when you add them up and divide them by how many data points you have, but the S value, the standard deviation, is now about 1.2. And then the third one, the distance between the data points are even wider, the difference. Therefore, it has a higher standard deviation. Here's an example. Estimating standard deviation. Without calculating, estimate the population standard deviation of each data set. But we're not going to do any math, and we can't, although we can just use an Excel and type to Excel that we have 8 points and they're all equal to 4, give me the standard deviation, it'll do that for you. But the objective for this question is, do we understand what standard deviation means, or which one is going to higher standard deviation than the other one? So here, the easiest one is the first one, because on the first one, all of the data points are equal to a 4. All of them are the same number. There is no change between these data points. So the standard deviation on the first one is a 0. So on the first one, each of the 8 entries is equal to 4. The deviation of each entry is 0. So sigma is a 0. Now, for the second population, okay, it's not the same number anymore. We have 4 numbers who are equal to 3, and then 4 numbers who are equal to 5. So the average for these numbers are still 4. So this is what 4 is. This is the middle number. This is the average of this population. So these data, they are one step away from the mean, and these are one step away from the mean. So for the second one, we can say that the sigma is equal to 1, because if average is given as 4, 4 is the average, and these two groups of data points, one group is one step ahead of the average, and then the other group is one step behind the average. Therefore, the sigma is equal to 1. So when we go to the third one, still we have this 4 as our average points. So these data points, they're one step behind, and these data sets, they are 3 steps behind. So that's a total of 4 steps behind. These are like 1 step ahead. These are 3 steps ahead from the average. So 1 step and 3 steps. Some of the data sets are 1 step away from the average, and some of the data sets are 3 steps away from the average. So that makes the question 3 to be about 2 standard deviation, because if you look at the average of 1 and 3, 1 plus 3 divided by 2 would be a 2. So the population standard deviation for this one will be about 2. If you actually use some technology and calculate the sigma for this data set, you will see that sigma is about 2.2. So estimation is really good. This is one of my favorite theorem in statistics. It is called empirical rule 68, 95, and 99.7 rule. This is a very important statistic knowledge. So even if you don't know much about statistics, if you show that you know this rule on any data-related job, you will gain a lot of reputation. So what this theorem says that if you have a symmetric bell-shaped distribution, so that's one of the rules that you can use this theorem. If you have a symmetric bell-shaped distribution, the standard deviation has the following characteristics. 68% of the data is within 1 standard deviation of the mean. 95% of the data is 2 standard deviation within the 2 standard deviation of the mean. And about 99.7% of the data will lie within 3 standard deviation of the mean. It's very important theorem. This is what the theorem is with a pictorial notation. So this is a uniform bell-shaped distribution. Sometimes you will see it as a Gauss distribution. When you have a uniform bell-shaped distribution, your average, your X bar is in the mean. This is the mean X bar. It's in the middle, okay? And then if you go 1 standard deviation above your mean, and when you go 1 standard deviation below your mean, 68% of your data they're going to be under this interval. They're going to be within this interval. If you go 2 standard deviation from the mean in each direction, now you will be housing 95% of your data within 2 standard deviation away from your X bar. Finally, instead of 2 standard deviation, if you go 3 standard deviation in each direction, you will be housing 99.7% of your data under this curve. This is called empirical rule. Here's the question how we're going to use this rule. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, ages 20 to 29, was 64.1 inches, with a sample standard deviation of 2.6 inches. Estimate the percent of women whose heights are between 58.9 inches and 64.1 inches. So let's try to understand here. We are working with a sample, and this sample is a group of women. Their ages are between 20 to 29, and their mean height is 64.1, and the standard deviation for this sample is 2.6 inches. So we want to find what percent, like is it 65% or is it 68%? We want to find the percent of women whose heights are between 58.9 inches and 64.1 inches. So don't forget, 64.1 is also the mean here. So if we just picture what this question is asking, the graph is gonna show the heights of women in the United States. Their ages are 20 to 29. So the mean average is given as 64.1. So the mean is always in the middle for a uniform shaped graph. And then we want to find out what percent of women are between 58.9 and 64.1. The distribution of women heights is shown. Because the distribution is bell-shaped, you can use the empirical rule. The mean height is 64.1. Now from this mean, if you go 1 standard deviation away, so the standard deviation was given in the problem, it was given as 2.6. So if you add 2.6 to this mean value, you get 66.7. If you subtract your standard deviation from this number, you get 61.5, okay? So this is your interval for 1 standard deviation away. So according to the empirical rule, 68% of the data is going to be between 1 standard deviation away from the mean. So this whole thing from 61.5 to 66.7, we're going to have the 68% of the data. But this question is asking me to restrict the shaded area between 61.5 to 64.1, which is the half of what the rule is telling me here, right? So we want to go back here, 61.5 to 64.1. We have the 34% of the data because half of 68 is 34% of the data. But then if we go 2 standard deviation away, we can find the 58.9. So we know that since this is a 95% total, 68 is in the middle, 95 minus 68 divided by 2, each one is going to be about 13 points here. So the expected answer here is 13.59 plus 34.13, which is about 47.2%, will be between 58.9 and 64.1. So that's how we're going to use the empirical rule. Again, I want to specify the empirical rule. And then if you understand what this graph says, this is a 34% of the data. This is another 34%. So their sum is 68%. So you're going to have 13.5% of your data on this tail, another 13.5 here, and 2.35% of the data will be here, and 2.35% of the data will be here. So this is called empirical rule, and this is an example. Now we're going to look at Chebyshev's theorem, which says the portion of any data set lying within K standard deviation, where K is greater than 1 of the mean, is at least 1 minus 1 over K squared. And when K is 2 in any data set, at least 1 minus 1 over 2 squared, which is 3/4 or 75% of the data will be within 2 standard deviation of the mean. If K is 3 in any data set, at least 1 minus 1 over 3 squared will be equal to 8 over 9, which will be the 88.9% of the data within 3 standard deviation of the mean. Now, why do we need another theorem which will tell us what percent of the data is 2 standard deviation away from the mean or 3 standard deviation of the mean? Because empirical rule only works if your data is in uniform shape. If your data is not in uniform shape, you can use Chebyshev's theorem. Here's an example. The age distributions for Georgia and Iowa are shown in this histograms. We want to apply Chebyshev's theorem to the data for Georgia using K equals 2. What can you conclude is an age of 90 unusual for Georgia residents, and explain. So for Georgia, mu value is given as 38.2 and sigma is given as 22.6. And the question is giving me that K value is equal to 2. So we're going to decide if 90 is an unusual. So K is 2. So we're going to think about 2 standard deviation. Mu minus 2 sigma, where sigma is 22.6 and mu is 38.2. We're going to get -7. But we're going to just round this up to 0 because we're talking about an age, and age cannot be a negative number. So 2 standard below the average, we just end up with the 0. Mu plus 2 sigma, so 38.2 plus 2 times 22.6 is going to give us 83.4. So 2 standard above the mean, 2 standard deviation above the mean, we get the 83.4%. Now, you can say that at least 75% of the population of Georgia is between 0 and 83.4 because of the rule that 1 minus 1 over 2 squared. 1 over 2 squared is 1/4. 1 minus 1/4 is 3/4, and 3/4 is 75%. So 75% of the population is between 0 to 83.4%. So an age of 90 lies more than 2 standard deviation from the mean. So this age is unusual. So this 90 does not fall between the 2 standard deviation interval from the mean. So it's going to be an unusual age. If you look at the standard deviation for group data, sample standard deviation for frequency distribution, S is equal to sigma minus x bar squared times f over n minus 1, where n is sigma of n, the number of entries in the data set. When the frequency distribution has classes, estimate the sample mean standard deviation by using the midpoint of each class. We're going to look at an example. Number of children in 50 households. So this is how many children we have in 50 homes. Some people have 1 child, some people have 3 children, some people have 0 children. And then I see some people with 6 children, some with 5 children. So you collect the random sample of the number of children per household in a region. Find the sample mean, sample standard deviation of this data set. So first, we're going to construct a frequency distribution. So we're going to count how many families are there for 0 children. And then according to the data set, we have 10 families like this. So 0 times 10 is 0. And then how many families with just 1 child? So in the data set, there is 19 of them. So 1 times 19 is 19. How many families with 2 children? 7. So finally, how many families with 6 children? 4 families. So their sum is 24. There's a total of 50 households here. And then this sum is 91. So if you divide 91 by 50, so 1.8 is the sample mean according to this chart. Now, 1.8 is the sample mean. So here though, instead of 1.8, they use 2 digits, 1.82. And now for the people who have 0 children, the deviation will be 0 minus 1.82. For the families with 1 child, the deviation will be 1 minus 1.82. So these are the deviations. When you square them, these are the deviations squared. And then when you multiply all of these deviation squares by how many families you have like this, we're finding x minus x bar squared times f. And then if you add them all up, you will get 145.38. And then if you just divide them by n minus 1, so 50 families minus 1, that's a 49 families. And then you divide them, take the square root. This will be the sample standard deviation for this grouped data. Standard deviation is about 1.7 children. So using the midpoints of classes, sales prices of homes. So we have this in $1,000. So they sold 19 houses where the price is 500 and more. They sold 129 homes where the sale price is between 100 and 199. So we want to use a frequency distribution to organize the data. Because the class of 500,000 or more is open-ended, you must choose a value to represent the midpoint, such as 5,099.5,000. So if you look at the graph here, the house prices are like this green area represents the house prices who are less than 100. This gray area represents the house prices where their house prices are between 100 and 199. So the first class is between 0 to 99. Second class is where the house price starts with $100,000 and ends in 199. So for these different classes, first they're finding the midpoints, and frequency is given in the diagram, and they're multiplying the midpoint of the class by the frequency. They're adding all these numbers, and then they're adding the frequencies, dividing that sum by the 390. 54.5 is the sample mean. And then when you take so here, you add them, and then divide them by this, and you get this. Now, here, x minus x bar, since this is the midpoint, 49.5, right? We have this x minus x bar values. So from the, for the class, the first class, 99, x minus x bar, and then x bar is 154.5. Yeah, they're subtracting this sample mean from the mid class, the midpoint of the class, and squaring them, adding them and dividing them by again n minus 1. That will be the simple standard deviation here when you want to use the midpoint of classes. So here's an example of how we're going to use this. Simple mean is $154,500 per year. An estimate for the sample standard deviation is given as 139.400. This one, oh, this one is the explanation for this question. Coefficient of variation, CV, coefficient of variation. It describes the standard deviation of a data set as a percent of the mean. So population data sets, if you have a population, if you divide your standard deviation by your mu value and times it by 100, this is called the coefficient of variation. When you have a sample data set, if you divide your S by your X bar and times it by 100, you're going to have the coefficient coefficient for your sample. So we have a table here. We have the heights and weights of the basketball team. The top numbers are the heights, bottom numbers are the weights. So the mean for the height is 72.8 inches with a standard deviation of 3.3 inches. So the coefficient of variation for this height is sigma over mean times 100. So it's 3.3 divided by 72.8 times 100. So it's going to be 4.5% here. But for weight, mu is given as 187.8. Sigma is given as 17.7 pounds. So the coefficient of variation using the sigma over mu times 100, you will get 9.4%. The weights, 9.4% are more variable than the heights because heights are varying by 4.5%, but the weights are varying by 9.4%. This is end of section 2.5.